Hey, what's up YouTube? It's Player 1011 here, and today we'll be talking about limits in our next installment on single variable calculus. So, today we're going to be talking about a rather simple concept, and hopefully this will make sense, because it seems complicated, but it's used to describe something that's relatively simple in theory. So, the definition of a limit is that a limit describes an output as an input approaches a certain point and gets arbitrarily close. So what do I mean by that? Basically what that means is that I'm going to use the red color here, that as this input x, here I'm going to put C, this is the specific point C, right? As I get really, really close on both the left here and the right here, the limit says, what number do I approach as an output, which over here is described as L, so I'll put L over here. And as you can see, that when I approach this point from the left, I am getting closer and closer to this number L. As I approach this number on the right, I also approach this number L. So that means that the limit, the general term here, the limit lim of x as it approaches C, the specific point, is L, the specific output. Now, this seems like a really complicated way of writing, just like input the number C into the function, you'll get your answer. And yes, you'd be right for most cases. So, as a general example, we'll take the limit as x approaches 2 of the function x squared. So, x squared is a very simple function. It's what we call a continuous function. And what that basically means is that I can draw it without picking up my pencil or, in this case, my mouse. And as it approaches 2 from the left and the right, since it's continuous, it'll approach the same number, meaning I could just plug this in. So, just as in most cases, I plug in 2, and 2 squared is 4. So the limit as x approaches 2 of the function x squared is 4. However, this doesn't work in all cases, so let's break this limit down. As you can see, this is the mathematical expression. I didn't write f of x here. I left it out. It's implied. The new thing that you don't see over here, that you see down here, that I'll introduce right now, is this negative sign over here, and then this positive sign up here. So, what this term means is that the negative sign means from the left. So the limit of x approaching C from the left, coming here, has to equal the limit of x approaching C from the right, coming here. So these are two different values, and I'll show you why right now. There's a second part to this function over here that I didn't describe before, and that is this, what we call discontinuity, and this is one of the many examples of where the limit does not exist, when there is what we call a jump. So, I'm going to approach this number, x approaching a. Now, when I come from the left, I approach this output value over here. I'm going to call this L subscript 1. Now, when I approach the value A from the right, I get a different value, L subscript 2. So, this value is L1, because coming from the left it's L1. Coming from the left, it's L2. And they're not equal, as you can visually see. Meaning that the limit does not exist at this point. So, now we're going to move on to a specific case of limits, and that would mean end behavior, which you may have been introduced to before you took calculus. Now, end behavior is the specific type of limit that describes a function as it approaches the ends on the x-axis. As x approaches infinity. And this is one of those cases where you can't simply plug it in. For example, what's infinity squared? Infinity is just a concept. It's not a real number. And this is important to understand for calculus. The concept of infinity means that it's not something that's quantifiable in the same way the number 2 can be quantifiable. Infinity is a concept of something that is endless. So, a polynomial function, as we described in the last video, is something that has a value on every real number on the x-axis, so it'll go on forever. The limit, describing the end behavior, describes how this graph acts as it gets closer and closer to these infinite values, or infinite extremes. Negative infinity and positive infinity, and then the same here. Negative infinity and positive infinity. So there are 4 things that you need to kind of remember. Now, first I'm going to deal with odd functions. Cubics, x to the 5th, x to the 7th, so on and so forth. Functions where the highest degree is an odd power. So when I write it out and I order them by degree, the highest degree should be odd for this scenario. And here's the second condition. The coefficient of that must be positive. So, for this case, I have ax cubed. And then I'm going to add plus ... because whatever's after that doesn't matter. So the end behavior over here is as such. So, I don't know why I wrote an F. Alright, lim, the limit, as x approaches infinity, that's how I write it, of, in this case, f of x, is equal to positive infinity. And you can see that visually over here. It's going to keep going up and up until it reaches some positive infinity, and it'll go up forever. Now, the limit, however, of x as it approaches negative infinity is actually quite the opposite, as you can see on the graph. So I'm going to quickly write this. F of x is actually equal to negative infinity. And as you can see, conceptually, as it goes backwards, it goes down and down and down forever. Now, let's say here's, we still meet the first condition, that the highest degree is still odd. It's still cubed, let's say, still 3. Now, let's say the coefficient of that is negative. So you have negative ax cubed, and then you have the same ... What happens is that you have, basically this graph reversed. So I'm just going to draw it quickly up here. A negative cubic function looks more like this. So as you can see, the limits are actually reversed. So I'm going to quickly write it out here. The limit of x as it approaches positive infinity, like so, is of f of x. Trying to keep all our terminology correct. That's actually now equal to negative infinity. So as you can see on the graph, as I go higher and higher on the x-axis, on the y-axis, I get smaller and smaller, not smaller, but lower and lower in value towards negative infinity. And it's quite the opposite. As I go to negative infinity on the x-axis, I go to positive infinity on the y-axis. So here, what I have is that the limit, I'm sorry if it's getting squeezed in, but hopefully my explanations will make it clear enough, of x as it approaches negative infinity of f of x is equal to infinity, or positive infinity, I should say. Now, that's the end behavior for an odd function. Now let's switch it. Let's say that the highest degree is an even number. So I have ax squared, and the coefficient now is positive. So that is basically what we have here. Just an x squared function with a positive coefficient. If it's positive, it means it opens upward. Now, for here, as you can see, the limit, and this is an even function, so which means that on the right side it's reflected across the same on the left side. So actually, what happens here is that the limit as x approaches infinity is equal to the limit as x approaches negative infinity. So I'm going to put negative infinity. And that equals positive infinity. Now, if I make this a negative, make the coefficient negative, what's going to happen basically is that all these values will become negative. So I'm just going to put this in a different color. What I'm going to get is something that opens up downward. So let's describe the end behavior for this. And I'll do that in purple just so it remains clear. Probably should have done that with the other things. Colors to make it clear. In the same way, the limits are still equal to each other, the two end behaviors, as you can see on the graph. So I'm going to write it out. The limit as x approaches infinity is equal to the limit as x approaches negative infinity. All right, negative infinity. And that is equal to negative infinity, as you can see on the graph. The output gets lower and lower in value. So that's the special type of limit that you'll see. Now another one is what we call an asymptote. So there are two types of asymptotes I want to cover. That would be a vertical asymptote and a horizontal asymptote. First I'll cover the horizontal asymptote, and this works in theory. I'm going to go a lot more in depth on this, maybe in the next video after this, when I cover fractions and finding the limits of polynomials when they're in fraction form. For example, x plus 2 over x plus 1, the limit approaching infinity of that. Obviously, that's not something you can plug in, so it's useful to know. But just describing this in theory, the horizontal asymptote can be described as a limit. So the limit as x approaches infinity, so of f of x, of this function here that you see on the graph, is equal to some value b. So if this is b, this means that as x gets bigger and bigger infinitely, it approaches this value over here. It never touches it, but it gets very close. Now, sometimes, and this is interesting, it can oscillate up and down. So if I draw it off to the side here, this is not something you necessarily need to know, but I like it. So that's your coordinate axis, and then you have your horizontal asymptote here. What can happen sometimes is that you get something like this. But it still gets smaller and it still approaches this value. As you can see, it may be oscillating up and down, back and forth, but it still approaches this one value at the end. So that is your horizontal asymptote. It's horizontal. Now, the vertical asymptote, it can never do this. So if this were vertical like this is, they don't cross the vertical asymptote. The vertical asymptote is a scenario where the limit does not exist. Or the limit is infinite, we call it. So let's do this in blue. Over here, you almost switch these numbers, and you'll see, I'll switch them for you. So the limit as x approaches b, and I'm going to write a subscript 1 because I don't want this to be the same value as b here. So b subscript 1 of f of x is infinite. Or it does not exist. So I could write DNE for does not exist. So if you remember, the limit only exists if it approaches it from the left and the right and approaches the same place. When I go to when I go from the right, it goes up to positive infinity. When I go from the left, it goes to negative infinity. They're not the same, so the limit does not exist. And we call this as a vertical asymptote. And what you see this most commonly in is fractions. So this will give you a hint to what is to come. 1 over x, when x is 0, if x equals 0, is undefined. And when you look at it on the graph, what 1 over x looks like, it looks something like this. As you can see, there's this gap over here at 0 where it's infinite. It never touches 0. That is called the vertical asymptote. 1 over x also has some horizontal asymptotes. It approaches 0. but this is just a hint into future lessons. That is your introduction to limits, and if you enjoyed the video, give it a thumbs up and a like, or thumbs up and a subscribe. I'll see you in our next installment of single variable calculus. I hope you enjoyed this video. Thank you.